Okay, and a good morning, and that was John Coltrane, right? And what were we listening to?
Crescent.
Crescent.
And the reason was is I totally did not understand any of your assignment yesterday, so I went and looked at the moon. And it was a beautiful crescent last night.
So I had you staring at the moon. Radicals will do that. And I'm referring to the material. Okay. Just from the standpoint of what we were talking about with the square root or radical symbol, there is a rather nice presentation on page 530. The 16th century German radical symbol. Okay, and the idea that it was probably derived from R and from the Latin root. And interesting, I can't pass this up, a reference to Leonardo da Pisa, Fibonacci. Now they give it as 1220. And so there's some question of when he would have used that. The book, let's see, Liber Bacchi was about 1206, 1204. So this was evidently a later publication. And the 1525 symbol, this symbol now on the right side, is argued that it was used in 1525, originated in France. So at any rate, the symbols have been around for some time. And so the question, of course, at this point, do you have questions on evaluating roots from last night's homework? Okay, so far
7-1.
7-1? Okay.
I got it eventually, but I guess I have to. I'm wondering if I did more than or made it work harder than I should have.
Okay, this is the two cars leaving. Okay. So we have two cars leave a place in Texas, Tomball, Texas, at the same time. One going north at 25, the other going west at 60. So that means they are at right angles to each other. And you want to know how far they are after 3 hours. And the diagram, in case you are having problems with north and west, is given to you. And so the question, what do you do? Well, at 3 hours, you'd have a 75 and a 180, correct? For your distances. Right, you'd have to know the distances. Does that answer?
That answer?
Yeah, because the argument would be, looking at this diagram, at 3 hours you have to know how long or how far each leg is. So one of them is going to be at 75, the other is going to be at 180. Then you're just going to use Pythagorean theorem.
Okay, I wasn't sure if that was something that would be incorporated into the equation or that was something you had to figure out first.
You have to figure it out first.
That's what I did.
I cannot picture anybody in Texas driving 25 miles per hour. I'm sorry, the problem loses a certain credibility at that point. Though quietly going home, right? Okay. Other questions on the homework? So this went well.
Not too bad.
Very good. Well, then we'll pass that one in and move on. And we'll get some of this going here in a moment. Wait for you to get some papers in. We got everything? The title of the next section is Multiplication and Division of Radicals. And most of the time we're going to think of it in terms of square roots. But just keep in mind that anything we say for square roots will work for a cube root, a fourth root. It can be generalized. On page 531, we have a product rule for radicals, and I'm going to see if I can shade that just a little bit. Now note, we have to have x and y non-negative. That goes. But the point being, the square root of x times the square root of y is simply the square root of xy. Now the question is, how can you verbalize that? The product of radicals is the radical of the product. The product of radicals is the radical of the product. Okay, that's not going well. Part of the reason for saying that is later on, and I keep talking about later on in mathematics, but if you were to go into something like a calculus class, there are a variety of things you have to memorize that fit in a very similar way. So to this extent, verbalizing something like the square root of xy equals the square root of x times the square root of y is nice, but it's even nicer if you can think of it as the product of two radicals. They have to be the same index, both of them square roots, both of them cube roots. But the product of two radicals will just be the radical of the product of the radicands. Now the radicands are what are inside the radical sign. But it's nice just to have that memorized. And of course, as you see in the statement, it can be written in two ways. I'm not quite there. I need one of those micrometer adjustments that allows me to just crank this up a little ways. Okay, what do we got there? There. But it can be reversed. It just says it's commutative. So either way you start. You can start with the product and factor, or you can start with the factors and multiply them together. Now, you have to be cautious of the square root of a sum. We talked about that a little bit yesterday, and there's a very nice disclaimer down here that we need to look at. I'll try to bring that down tight on the focus. Okay, let's go to that statement. The square root of x plus y cannot be broken apart. It only works with products. So you can't say that you'll break the square root of x plus y into the square root of x plus the square root of y. Seems like it might be logical to do that, but it won't work. What about quotients? Okay, if you were to, again, try to say this in a verbal sense, and let's try it, Debbie. This just doesn't come across all that great. But the quotient of two radicals is what? The radical of the quotient, and if we slide over, it just goes the other way. You can break them up in either fashion. And again, that didn't help. That's about as good as I'm going to make it. Now the question is, how do you make that work for you in terms of problems? There are times when we would like to simplify a quotient that involves a radical. Let me just give you a couple examples. I'm going to do that on the board. But let's think of something like the square root of 7 over 25. The square root of 7 over 25. So the square root symbol is here, and I have 7 over 25. And the idea is that you can simplify that. And so there's going to be a generic phrase for many of these problems with radicals to rewrite it as the square root of 7 over the square root of 25. And then what can I do to the square root of 25? Simplify that simply as 5. So this becomes the square root of 7 over 5. And that will be considered the better form. Hence the phrase, simplify. So we would put up here, simplify, and what would be expected is that you understand this is a better form. Now, there's another little comment here, sort of a parenthetical comment. We have rationalized the denominator. Now, technically, the square root of 25 was a rational number. And so one of the questions that comes out of that, if I looked at the problem in a different way, and let's say I had this one to simplify now. Okay, coming down here, again, this is still the square root of 25 over the square root of 7, and that is 5 over the square root of 7, and this is not considered acceptable, whereas this was. The denominator is a rational number here. It's not a rational number here. It's irrational. And so what we're going to do is multiply the denominator and numerator by the square root of 7 and get, finally, 5 the square root of 7 over 7, and that is now going to be considered a better form because the denominator is a rational number. The square root of 7 was not, but the square root of 7 times the square root of 7 is 7. And just a comment here. When you look at the square root of 7 times the square root of 7, you could argue this, because that's true by the product rule, right? And then you could argue that is 7, which is where this number is coming from. However, the square root of 7 times the square root of 7 is just 7. That's coming back to the statement, if you have the square root of x times the square root of x, where x is what? Non-negative, then we argue that that's just x without saying the square root of x squared. Now, this is a minor point. If you're comfortable with this statement, and you can go from here to here immediately without doing this, you got the idea. If you feel you must first write it as 49 before you can pull out the 7, that's not so good. Very subtle. Get the same result, but I'm again trying to convince you that this is a much better form to think than this. This tells me you're firing in all 8 cylinders. You're short-circuiting here a bit and doing an in-between step that tells me you aren't pulling the pieces together at the level you should to go on. Very subtle point there. But this is, again, under the phrase simplify. Let's come back and contrast these two. Very similar. The question is, what do you have at the end? When I ended up with the 5 down here, that was good. Stop. End. You're done. But here when I got 5 the square over the square root of 7, I was not done, and I had to do what? Rewrite it so I had a rational number in the denominator. The difference between those two problems is very important, because there are very implicit rules involved here for what's acceptable and not acceptable. The argument, by the way, for why this is better, dividing by 7 is not so bad. You're dividing by a whole number. Dividing by the square root of 7, which is a decimal that'll go on for eternity. Where do you stop it? How do you know what kind of error you've introduced? This is a much preferred division. And that was why it was argued that leaving a square root of 7 in that denominator was not a preferred form. 20 years ago, the argument was a very important one, because if you had to get a decimal for this, you didn't have an alternative but to, maybe 25 years ago, do long division. With the current calculator, you could carry it out pretty easy, but this is still going to be argued as a preferred form. Now, the key is to simplify a radical, and the comment I made a moment ago about the square root of a times the square root of a, the square root of x times the square root of x, this is stated here in a little different form. This is on page 534, where it states the square root of a squared is a. Assuming what? A itself is non-negative. That's critical. Okay? Because technically, if I had the square root of negative 2 times negative 2, Think of that for a moment. The square root of negative 2 times negative 2. That would be the square root of 4, and we're arguing that that is a 2 if I don't put anything in front of the radical sign. So taking this statement here, if I take the square root of negative 2 times the square root of negative 2, that's the square root of negative 2 squared, which is the square root of 4, which is 2, but that wasn't the number inside. So the argument is the square root of x squared is x if x is non-negative. Otherwise, we have the possibility of what? A rather confusing state of affairs up here. So again, our assumption will be that whatever is done inside these radical signs, that they will be non-negative values. So we are going to assume that any x, any variable you see inside the radical sign, will represent a non-negative number. The properties that I mentioned earlier, square roots, I said could be generalized. This is done for you in the bottom of 534. So the nth root of x times the nth root of y is the nth root of xy. Again, the product of radicals is the radical of the product regardless of the index, but the index must be the same, the index in each case. So as an example, if I said I had the cube root of 4 times the cube root of 2, then I can argue that that's what? The cube root of 8. By the way, what is that? It is 2. But if I take the cube root of 4 times the square root of 2, you're done. Nothing can be done. This is understood to be the second root. The index is not the same on each radical, and so this is it. End of story. Nothing can be done here. Okay, now in the same way, if we come back to the text, and let me slide over. Okay, that's okay. I'll just slide while you're there. Slide over. Here is the square root symbol, and notice the restriction. The denominator cannot be 0. So the y value is going to have to be greater than 0. The numerator x can be non-negative. So those are just generalizations. The little glitch that you're going to have is when you see a radical, you're going to be inclined to say root 4 instead of square root of 4, or radical 4, and think square root when you see radical. And you're going to get caught if we again come back to this problem right behind me where I have the cube root of 8. That cube root of 8 can be written as 2, but if you're seeing that as a square root of 8, then you don't seem to have anything you can do, technically. Now the question, how do we think of simplifying expressions? Let's look now at the square root of 8 for a moment. Now the argument is that that is not in the best form, because 8 contains a perfect square. I can rewrite this as the square root of 4 times the square root of 2. I factored the 8 into a perfect square. So I'm saying that once I factored it, I can write it as the product of those two radicals, but the square root of 4 is 2, so I have 2 the square root of 2, and that will be considered a preferred form. The argument, if I know what the square root of 2 is, which is roughly 1.4, it's 1.414, then if I know this, then I know immediately that the answer is going to be 2828, because I was able to simplify the square root of 8 into an easier problem, and by knowing the square root of 2, I can get my answer quickly. That was the argument for doing it. Now, many of the arguments that we're presenting here are BC, before calculator. where you had to do some simplification or you were in trouble. Now, there are certain problems that don't lend themselves to the technique very well, but anytime you can factor something into a perfect square, do so. So, for example, let's do another one. The square root of 98. What do you see when you see a 98? Anybody? No. I looked at Perry's cap.
Perry?
The Niners. Two times 49? Yeah, I mean. Okay, so what's the square root of 49? 7. And so I now have 7 the square root of 2. And note again, if I know what the square root of 2 is, I'm quickly going to find this just by doing that product. Okay? Walking around knowing that that's 1414? No.
So we can leave it at 7 square root.
But the motivation for why you would do that, by knowing a few square roots, you could simplify things rather nicely. This would be considered a simplification. So again, question, why would you do simplifications like that? There's obviously the answer I've tried to give in terms of getting numerical values in decimals. But what if I had 7 plus or minus the square root of 98 over 7 for a solution to a quadratic equation that we talked about yesterday? Do you see why it would be nice to simplify? Because now you could write this as 7 plus or minus 7, the square root of 2, all over 7, and that allows you to simplify rather nicely into 1 plus or minus the square root of 2. Okay? A 7 here, a 7 here. I can take a 7 out as a common factor, a GCF. Cancels with that 7 and leaves me 1 plus minus the square root of 2. That's not appealing to everybody from the looks in your faces. Can I answer a question there that would...
Do I look that blank?
Yes. The answer, honestly. Okay, Jennifer.
Yay.
You say you cancel the 7 with the 7 on the bottom?
Uh-huh.
Wouldn't that leave us a 7? So you divided.
Wouldn't that leave?
Okay, let me bring this down here again. I have 7 times 1 plus or minus the square root of 2, all over 7. Is that reasonable? There's a 7 there and a 7 there. This is one of your favorite problems.
It is.
This is AC plus BC, and you take out the C and have A plus B left. This is Jennifer's factoring. Now what can I do with the 7s?
Cancel them.
Cancel them, good. And that's just got a 1 underneath it, and the 1 can be thrown out then, and I just have 1 plus or minus the square root of 2. See, this went under the phrase okay, good. If I wait long enough. Simplify. And simplify may mean it's harder to do than it was to leave it the way it was. Now again, there's probably a very strong argument for saying with the current calculator, just do it. But now we're going to have to appeal to the aesthetic sense of mathematics. That this should give you a warm, fuzzy feeling. And this, not as nice. So the aesthetics say this is much nicer. That's part of the justification. Because with the calculator, there's an argument that some of the things we're doing could be avoided. Okay, let's see what I can do that I'm going to show you a problem. It's very similar to my 2 and 4 problem where I had the cube root, and I just want to bring this up again as an issue. This is on page 535. Yeah, the cube root of 7 times the cube root of 49. I'm on 535, example 8F. And what you have to be alert to is that 49 is 7 squared. So my point is, if you're looking at a cube root, you have to have a predisposition towards getting a third power somewhere to make this all work. So the simplification is we slide over. When you get the cube root of 7 cubed, then you know your answer has to be 7. Now I'd like to talk about that for just a moment. The cube root of 7 cubed. So we come to the board whenever you're ready, Deb. Thank you. Now you've got to feel good about that being 7. Does that help it? The cube root is the same as the 1/3 power. So 7 to the 3rd to the 1/3, now you multiply the exponents, you get 3 times 1/3 is 1, and therefore 7. More or less. Let's go back to the book. That's the idea there without going to the fractional exponent. Okay, coming off there, what about variables? If we want to simplify something that has a variable in it. So I'm going to look at a couple examples. These are now on page 534, and these involve expressions that may or not, I don't know, it depends on how comfortable you are with the expression here. I'm looking at the middle of the screen now with part C, the square root of r to the 9th. Now you are expected to write that as the square root of r to the 8th times r. Then break that up into the square root of r to the 8th times the square root of r, which is r to the 4th times the square root of r. Okay, let's come off there for a moment. My question. What is r to the 4th times r to the 4th? R to the 8th, right? So the square root of r to the 8th has to be r to the 4th. Let me back up a step further. The square root of 25 is 5. Why?
Just 5 times 5.
Good. The answer, the square root of 25 is 5 because 5 times 5 is 25. So the square root of r to the 8th is r to the 4th because r to the 4th times r to the 4th is r to the 8th. Okay, let's try r to the 8th to the 1/2. R to the 8th to the 1/2, and 1/2 times 8 is 4. That, again, may make it easier for you to see. Let me try a little different one for you. Let's say I ask you to take the cube root of r to the 9th. Not the square root of r to the 9th, but the cube root of r to the 9th. Anybody want to take a chance? Again, the cube root of r to the 9th.
Square root of 3?
What?
Square root of 3?
How can you get a square root when you're talking about cube root?
Because it's 2 times the square root of 4. I mean 9 and 9.
Wait! got lost in that.
Square root of 9 is...
Debbie, we're going to have to go to the sideboard. I want the cube root of r to the 9th, not the square root of r to the 9th. Let's come back to the problem on the screen. That was the square root of r to the 9th, and I've just tweaked it a little bit. The cube root of r to the 9th. I think Jennifer woke up.
It's r squared times square root of
The cube root of 9, which would be r.
So we go
R squared
the
times.
cube root of r to the 8 times the square root of...
Can you have the square root when you've got a cube root? Now that's the thing I'm trying to get a little bit concerned about here. You're saying you have the cube root of r to the 8 times what? But what of r?
Of square root of r.
No, cube root.
It has to be a cube root again.
Cube root of
You see where you're having a tendency to get trapped? You're saying cube root one moment, and then you're going to do what? Say square root the next minute. And you've got to be careful because that's going to have to be the cube root of r also. What is the cube root of r to the 8?
r is
That would be r to the 6.
You're telling me r to the second. Okay, let's try it. What is r to the second times r to the second times r to the second?
R to the 6.
r to the 8.
Is that r to the 8? See, you're making a statement that works here. This is 2. But this doesn't work coming down to r to the second. Let's come back up here for a moment. What?
r to the 30.
Yes. Because what is r to the third times r to the third times r to the third? R to the 9th. Now, there isn't again, let's go back to the document camp. Because all I did was take a problem, which was the square root of r to the 9th, and we said that was pretty straightforward. We made it a cube root r to the 9th, and it went up what kind of difficulty level? Maybe a factor of 2 or 3? A lot more difficult because you were wanting to get what? An 8 here, but that's an exponent, not the number. So if you look at the cube root of r to the 8th, then you say, that's r to the second, then you better be able to do what? Take r to the second times r to the second times r to the second, that is, r to the second cubed, and get what? R to the 8th. But you don't, you get r to the what? 6th. Now let's go back to the other little concern. When you have a cube root of something and you want to write it as a product of radicals, what must you do? Keep the index the same. So if you say cube root in the first one, you've got to say cube root in the second one. But notice how easy it is to say what? Cube root of r to the 8th, square root of r. And get caught. Okay, back to the document cam. Now, there is, in the problem right above it, the square root of 25m to the 4th. You see where that's coming out 5m squared. I hope that looks okay. Okay, let's see if we can find just some problems that are intriguing and know how to do them in a way that we'll just choose sort of potpourri here, having some fun. Okay, let's try going to number 12. The square root of 10 times the square root of 15. Now, what can you do there? Well, you can see that as 150, right? I'm going to write the problem there. We're just going to look at different ways that you could simplify that. You're asked to do a product rule. We have the square root of 10 times the square root of 15. Now, directly you could say what? 150, agreed? But you have to see 150 as what? What? Think money. How many quarters for $1.50?
6. So 25 times 6.
Okay, that's not working well. I can tell. We're in trouble. That's what I was wanting you to see. Mm-hmm. The perfect square. What do I do with the square root of 25? So I can have 5 the square root of 6, and that will be considered the best answer. Okay, is there a better way to do this? The directions said use the product rule. But if I use the product rule, there's another way of looking at it. Let's try it this way. What did I do? Prime factored, right? Now what can I do by noticing these are both what? The square root of 5 times the square root of 5, which is? The Lieber. The square root of 5 times the square root of 5 is what?
5.
Not 20. You don't even think 25. Think 5. Square root of 5 times the square root of 5. Who's buried in Grant's tomb? So we have a 5, and then what is the square root of 2 times the square root of 3? Square root of 6. Can I have the same answer without having to do what? Break the 150 into 25 times 6. I think this is easier than this is. Is there discussion there?
How do we know which one to use? Like you just picked 25 and 6. How do we know which one to use? Like
You have to have, basically, go back to Michelle's question. I see a 150, and I'm supposed to pick perfect squares out of there. So what do I have to run through in my head? 1, 4, 9, 25, 36, 49, 64, etc. And then I hope I find what? Something here as a factor here. And that's what I end up doing. I just run through in my head the perfect square and say, okay, is there a perfect square that is a factor of the 150? If this does not appeal to you, then you can go to what? The prime factoring idea and break it into smaller pieces and then recombine it in a clever way. Does that make sense? Okay, next, back to the document cam. Let's see if there's another one there. It's not looking very productive. We need to get something more exciting. Well-seasoned. Let's see. Okay, let's see if we can get this one as I slide over 11. Break it into pieces first. The 6 into what? 2 and 3. The 15 into 3 and 5. So what's your answer? 3 the square root of 10. Okay, 14. And just look at it and immediately give me the answer. You better see 17 without saying 17 times 17. Okay. Coming out there for a moment. That one was for Michelle. I'm sorry. Not really, but I'll say something.
Something like number 15. That
15. 15.
That would be the square root of 13r, right?
Okay, on number 15. Yeah, just the square root of 13r. And there's nothing you can do. But notice the restriction, r greater than or equal to 0. Okay, coming off that for a moment, let's get a little more fun here. I want something to really, 32. Whoa, okay, let's come off there for a moment. That didn't work well at all. See if I can, there, I got the shadow out. Okay. The square root of 50 times the square root of 72. That's the challenge. Let's see what we get. So we have the square root of 50 times the square root of 72. Okay, a lot of ways of approaching it. Can you give me the most efficient? Somebody go for the most efficient factoring. And don't think in terms of multiplying 50 times 72. That would be very bad.
Root of 2.
Okay, so 2 and 25. And what do we see for 72?
2 and 36.
2 and what? Did you say 36? Okay, I didn't catch it. I got the 2. I didn't catch the second number. Is that good? Does that make you feel good?
So your 4 times 4 times
So what's your answer? Okay, square root of 25 is 5. The square root of 36. Square root of 2 times square root of 2.
2.
60? Now, if we'd multiply, this would come out nicely at what? What's 60 times 60? So we would have had 3,600. We had to. Because whatever the square root is has to be 60. So inside has to be 60 squared. Hmm. 60 must be the square root of what number? 60 times 60. Yes? Hence, 3,600. Okay, back to the document, Cam. Okay, that was the one right above it. 3 times 18. What do you get? Or what would you recommend there? Just looking at square root of 3, square root of 18. Okay, you have 3 times 6 for 18, correct? So that might be the best way. The square root of 3 times the square root of 3 times the square root of 6, which would be 3 to the square root of 6. Are you following me on that statement, I hope? Okay, time for quotients. We've been having all that fun with... Oh, no.
I was having so much fun.
Yeah. Okay, I like 45. Okay, I need to bring that up just a little bit. That helps. Okay, what are you going to do? Look at it, think about it. Just want you to think for a minute. Don't get too caught up in just, there are different approaches you can use. So I have, in 45, 30 to the square root of 10 over 5 to the square root of 2. Now what's, I hope, very clear is you can take 5 into 30. That's the obvious part, I trust. Now what are you going to do with the square root of 10 and the square root of 2? Two ways of doing it. One approach. That works. True.
Divide the square root of 2 and the square root.
Or square root, so you can bring the fraction underneath. This is the quotient of the radicals. This is the radical of the quotient. And 2 into 10 is 5. And you get 6 to the square root of 5. Not a case where there's one only way to do it. You have a choice. Any discussion there? Okay, I'm curious what Debbie's reaction to this is today.
That one I liked.
That one you liked? Oh, what about the ones before? Or do you, okay, this is I got this kind of thing. Okay, let's go back to the document, Cam. We took care of that one. Now, let's see what we can, the one right above it. Let me slide that just a little bit. Okay, in your head if you can. And you do it in your head, just staring at it. This is the butterfly technique. You stare at it until the butterfly flies by, and then you grab at it. Okay? Okay, I heard an answer of 10.
1.
Only 1 10, 2 10s, 3 10s. Okay. I like the 10. But the question is, how do you see that? The problem was the square root of 10 over 13, and then we sort of put it, I guess, in the middle, 130. Break things up, that would be one approach, right? Does that work? And the square root of 10 times square root of 10 is? 10. Is there another way you could see it? Could I have instead said that is the square root of 10 times 130 over 13? That would have been allowable. And the 13 would have gone into here 10, and 10 times 10 is the square root of 10 squared, which is 10. Okay. Or I could have said the square root of 130 times 10 over the square root of 13. I don't know if that works as well. And then gone to, I guess, probably at that point say, well, I have 1300 over 13, but that is the square root of 100, which is 10. Now that works. Which is best? But this works. Now what you're hunting for is some way to avoid this and try to get where sometimes you can see it in your head without a headache. Okay, back to the document camp, because we've got more interesting stuff to do. Oh, let's see what delights are there. 74. Let's see if I know if that's about maybe a brick on the book. Okay, 74. What are we going to do with that one? We have the cube root of 25p times the cube root of 125p cubed. Now don't be too quick. On these, look at what you have. Now, what in that problem jumps out at you, I hope? We're just staring at it. Just stare at it. This is sort of like a mantra. I will see it. Okay, what did you see? We come on. What?
A 5.
Why a 5?
Oh.
What did you see?
I see 125.
Okay, 125, which is a perfect cube. That was the key. Why would I look for a perfect cube? Because I have a cube root. What else jumps out at you coming back to the problem? The p cubed. Because the cube root of p cubed is the variable itself. So what does that second radical simplify to? 5p. You're done. Back to the problem.
How do you write it?
5p times the cube root of 25p. All you could do is write the second radical as 5p. So this becomes, right here, this 5p. So you're going to end up with 5p times the cube root of 25p. And there's nothing else that can be done to that. Now what I'm trying to get sort of setting here in a mental state, look, think, keep looking, keep thinking, and say, is there a shortcut? Am I seeing something that maybe I can do? Because if you take a direct approach, and if you were to multiply all this out, what would you get as we look at it again? Not 625, but 3,125 p to the fourth. That's getting you nowhere except trouble.
So for our notation on the answer, it should be the 3 cube root 25p times 5p.
Okay, I've got to stop. Let's go and come over here. Thank you, Debbie, for thinking that. On 74, we're talking about the answer now. So number 74, can you write down what you said, Barry? Your answer? What were you doing?
I asked if would the answer be the 3 cube, the cube root,
of?
right, of 25p times 5p?
Okay, gotcha.
Is that correct? I guess that's what I'm asking.
Good question. Preferred, put the 5p in front of the radical, because what would happen if I wrote it the other way, the way you originally said it? You wouldn't know whether the 5p is part of that radical or not. So if I put this 5p at the end, I had an instructor in graduate school who dropped a little notch at the end and said, that's it. That means whatever's behind that works. Because oftentimes, how do we write square roots? A little bit like a check mark, they just sort of trail off into the horizon, and you're not sure what's underneath or not. So it's very common, if you have something multiplied by this, put that other factor in front of the radical, then it's not confusing. Excellent question. Something I should have picked up on. So the 5p would be written in front. That is much less confusing, much better form. So let's go back to the problem again, Debbie. Very good question. Wish I'd thought of it. Now, there was another one I wanted to look at, just with the idea of, at times, you need to understand nothing works. Okay, 71. There's nothing that you can do with this problem to make it any better other than to say what? The fourth root of 12. End of story. This fourth root of 12. And that's it. Now the 67th one right above it, what do you see? The 125, the perfect cube of 125, I think you see without a problem. The 216 I'll let you figure out. But note, the cube root of a negative number can be negative, will be negative. Now the square root of a negative doesn't exist in the reals. But the cube root of a negative will be negative. This set is going to probably frustrate you to the extent that it doesn't seem like every problem you look at, you know precisely what to do the minute you look at it. It is a little bit more, look at it and find the best way. There's more than one way that you could achieve the answer. So, how did we do in terms of time with last night's homework? I need to have, was it a reasonable amount of time for the problems, or a bit long in tooth? I bet. Yes. Now this is a person who will sit at a computer for hours and work on a problem with a computer. Yes.
I was taking his time with the computer. It wasn't that fast.
Okay. Well, what I'm thinking is, my first reaction on these is to go 1 through 74 odd. Now, the part that I'm a little bit concerned about is whether or not that is going to be, given the nature of the problems, a little bit long again, because if you see them and you get into it, my guess is a half hour and you're there. If you don't, then you could easily be in an hour, and that's not bad. If it's really bad and it takes you an hour and a half, that's still not bad. If it takes you 4 times longer than I'm thinking, that's getting a little bit long. So I'm going to gamble on the fact that it's somewhere in between 1 through 74 odd. Okay, John Coltrane's where we started, and what did you choose for a close, Debbie?
Since we started out with the miles problem with yesterday's problem, I picked miles mode.
You want us to go back to word problems after all this fun with radicals?
No.
Okay, have a great day.